Okay, welcome to the second part of lecture 3. In the last lecture, we talked about observers. I gave you a brief introduction of what observers are and what is the use. We basically want to implement the state feedback law U is equal to minus kx in order to arbitrarily place the poles of the system. But since x would not be available for measurement, so instead of using a state feedback law U is equal to minus kx, we are thinking about implementing a state feedback law U is equal to minus kx hat, where x hat is an estimate of x. That means the problem changes to basically observe or estimate x. Observe or estimate x. And the systems or the simulations that give you an estimate of the states are called observers. We saw open loop observers on the last turn. What are open loop observers? Just for a brief recap, you have a system which is similar to the original plant. That is, you have the original plant A, B, C, D matrices and some initial condition x0. You try to create a similar computer simulation. A, B, C matrices are known, and you assume that you also know the initial conditions to which the plant responds, and then you can basically estimate, given same inputs to both of them, same input u here and the same input u here, you can get an estimate of x in terms of x hat in the open loop observer. But we saw in the last turn that open loop observers have no error control, because if there is some problem in the initial estimate x0, the initial estimate x0 is not x0, it is something else, say x bar 0. The initial condition is not known accurately. Then what will happen is that the estimate x hat t would not be equal to xt, and this error xt minus x hat t would continue, this is an error, would continue to grow as time passes. You can understand it like this. A simple example would be like, if you have an initial line which goes like this, and this initial condition is not properly estimated, and you start from some other initial condition, you may end up diverging a lot. So the initial error would be small, but as time proceeds, the difference between the two xt and x hat t might be large. So what is the solution to this is what is called the Lewinberger Observer. What is the Lewinberger Observer? It may sound to be a difficult name, but actually the concept is very small, very simple. The concept is that you have this plant x dot is equal to ax plus bu, and here you have your x, then you multiply this with c to get y here. This corresponds to an input, and here you have an open loop observer. Again, x hat dot is equal to ax hat plus bu. This is your x hat, this is c, this is y hat. So why not, since y is available for measurement, why not use this y information? The concept is, why not use the y information, use the y information to improve the estimate of x. See, in the open loop observer, you are not using this information. You could always check the difference between y and y hat to see whether your solution is, whether your estimate x hat is equal to or near x. Because if x hat and x diverge, then there is a very good chance that y hat and y would also diverge. So the concept is, why not use this information of y, which is available because y is the output which is available for measurement, and then use it to design an observer which is better. So this is what is called the Lewinberger observer, and the equation for this observer is given by x hat dot is equal to ax hat plus bu. This was your open loop observer, and then you add a term in this y minus y hat. So you add these dynamics to this just to incorporate these dynamics and see what effect does it have on the observer. So this is the equation for the Lewinberger observer. Now, how is this going to help you? How is this going to help you in having a better estimate of x? Now, let us try to first find out the size of the matrix M. Now we are assuming it's a seesaw system. So it's a seesaw system. So that means this is, and it is an n order system. So this is going to be n cross 1. So M has to be n cross 1 because this is 1 cross 1. So M is actually a column matrix, right? With n entries. So how is this going to help us in having an estimate? Let us look at the error dynamics. What are the error dynamics? We define an error term. We call it x tilde is equal to x minus x hat. This is the error. Why is this the error? This is the error because x is the state and x hat is the estimate of the state. So what would be the dynamics of this error? How is the error? When I say error dynamics, what I mean is, how is the error changing with time? How is the error changing with time when you use the Lewinberger observer? So if you see that the error dynamics converges, that means the error becomes 0 very fast. That means your observer is good. And if your error dynamics diverges, that means you have no control over the error. Then that means your observer is poor. So let us look at this equation. X tilde is equal to x minus x hat. Let us differentiate this. So x tilde dot is equal to x dot minus x hat dot. And let us now use the two equations that we have and put them here. So one equation is equation of the plant. So x dot is equal to ax plus bu. This is the plant that we are having. So we can use this equation here in this. So this is ax plus bu, and x hat dot is your observer here. So this is going to be minus ax hat plus bu plus m y minus y hat. This is the equation of your observer. And let us try to simplify this a bit. So this is going to be ax minus x hat. This bu and bu, this will vanish. They'll subtract from each other. And you'll get minus m y minus y hat. Now you already know that your y is equal to cx. In a similar way, your y hat for the observer, the second equation for the observer, the output equation for the observer would be cx hat. So you can substitute these two in this. In fact, we have written this second equation for the observer here, that y hat is equal to cx hat. So you can substitute this here and you get ax minus x hat minus m, and you can put the c out, you get x minus x hat. So you get a minus a minus mc into x minus x hat, and this actually means x tilde dot is equal to A minus MC x tilde. So this is your error dynamics. This tells you how is the error going to change with time, right? And since M is in your control, since M is in our control, we can place the poles of A minus MC, or in a to say it technically in a more correct way, we can place the eigenvalues of A minus MC. Eigenvalues of A minus MC, so as to have a fast convergence to 0 of x tilde. What would that mean? That would mean, say for example, you're able to make your A minus MC such that your x tilde is initially high and then it becomes 0 very fast. What this actually would mean is that there is an initial error in the estimate or in the measurement of the initial condition. So x0 and x tilde 0, there is a large difference here, which the difference is here because that is reflected in the large initial value of x tilde, and because you are able to control the error with the help of M, as the error dynamics using the Lewinberger observer is this, you are able to make this error 0 very fast. So when x tilde becomes 0, that means at that point x0 and x hat 0 would be same. X hat 0 would tend towards x0. I hope it is clear. So how do we actually place the poles of, so if our error now is, error term is x tilde is equal to A minus xc x tilde dot x tilde, let us assume that our A of the original plant is like something like this: 0 0, a third order system, minus A0, 1 0 minus A1, 0 1 minus A2. So let us suppose that our original system has A in the observable, all the matrices A, B and C. So the original plant has A, B, C in the observable canonical form. It's of size 3 cross 3. So our A is this, our C is in the observable canonical form, our C would be 0 0 1. So our A minus MC for the observer now, for the error dynamics, would be 0 0 minus A0, 1 0 minus A1, 0 1 minus A2, minus M. M in this case is going to be M1, M2, M3. It's going to be a tall matrix. C is 0 0 1. So A minus MC is going to be 0 0 minus A0, 1 0 minus A1, 0 1 minus A2, minus, now you can multiply these two and you'll get all these zeros, these terms here, and you have M1, M2, M3. Better to call this M0, M1, M2 in order to have a more easy to remember relationship. So this is M is M0, M1, M2, M0, M1, M2. So your M is actually, the M matrix is M0, M1, M2. And when you do this, you get 0 0 minus a0 minus m0, 1 0 minus a1 minus m1, and 0 1 minus a2 minus m2. So the original system had a characteristic equation. You can see that from the A matrix, the original system had a characteristic equation given by s cube plus a2 s square plus a1 s plus a0, and your observer dynamics and your error dynamics have a characteristic equation given by this matrix, which is s cube plus a2 plus m2 s square plus a1 plus m1 s plus a0 plus m0. So with the help of m0, m1, m2, right, m is equal to m0, m1, m2, you will be able to modify the error dynamics. You'll be able to modify this characteristic equation in order to get the characteristic equation for the error dynamics that you require. And that characteristic equation might be the one in which you're ensuring that your error falls to 0 very quickly. And because of that, you will be able to obtain a convergence between x0 and x. So actually what we are doing, we are designing m here in the observer that we wrote down. This m that we are designing is such that the error dynamics which has this equation is what we want it to be. And if we are ensuring that the error converges to 0 very fast. So how would this Lewinberger observer look if we have to actually draw it? If you have to actually draw it as a system. So if this is your actual system, this is your A matrix. You have x that goes in, you have ax that comes out, and then you have you sum it up with, there is a u that goes in to the B matrix. So you have this bu that comes out, and you sum, this is your ax plus bu here at this point, and this ax plus bu, you're taking it, this ax plus bu, you'll be taking it back. So ax plus bu is x dot. So this is your x dot, you'll be integrating this, and after integrate this you get back to x, and this x here that you have, you multiply this with c, right, and this multiply this with c, you get y. So this is your system, x dot is equal to ax plus bu. And now what you're doing is you have a similar system here also, but the variable is x cap. So x cap gets multiplied to a, you get ax cap, then you have a summer here, and you take the same input, this input u that is here. So let me draw a bigger line for this u. So this u is here, right? So you take this u from here, you multiply this u with b, you multiply this u with b, and you get bu, sum it up here, so you get bu. So this gives you x hat dot, and then this x hat, you can this x hat dot, first you take it back, right, integrate it to give you x hat, and this x hat again you multiply with c to give you y hat. Now this would be your open loop observer, in which you are not basically looking at anything. You don't know actually whether your system is converging or your system is giving you a good estimate of x. So this portion is your open loop observer. You have a good estimate of A, B, C matrices, and you basically start with the same initial conditions. But the Lewinberger observer is when you're using this y and this y hat information, and what you're doing is actually you're taking this y minus y hat, right? So you're taking this y hat back up. Say for example, let us draw this now with a red pen. You're taking this y hat back up, so you're just taking this y hat back up, and you're subtracting the two, y and y hat. You're multiplying this with m, and this you're basically using at this summer here to give you x hat dot. So this addition in red makes this open loop observer the Lewinberger observer. So this Lewinberger observer and this addition of this y minus y hat information in this ensures that the error dynamics are A minus MC x hat dot x tilde dot is equal to A minus MC x tilde, and by ensuring that the error dynamics are like this, you are basically able to control the error by arbitrarily placing the eigenvalues, of the error. So basically you can control the error in the initial estimate of x as well as you want it to be. You can ensure that the error becomes zero as quickly as you want it to be. So this is very similar to the control problem that we solved in the last turn, and we'll see that solving the observer problem on one system is similar to solving the controller problem on the dual system. This we'll do in the next part of this lecture.